It should be in there.
So this is display, right?
It doesn't say anything. Maybe can drag and
setting of display.
You need to disable the mirror. Choose mirror instead of duplicate. No.
Display. Okay. No, not working. Is it possible that they okay. I have a flash disk. Oh my god, I can copy the flash disk.
Is there a microphone?
Yeah, you know that you must can you use my laptop?
We're going to stop screen sharing. Everyone in live audience needs your laptop.
Ah,
There you are.
sorry. So, yeah.
But for the speaker,
So this is two CO or what is it? NATKLCO.
we just have slight technical issues, so there's going to be a short delay.
Did you get it?
Yeah, I'm on. Going up my, you know. No, I'm not. I'm on. I'm just going up this stuff.
The talk is 20 minutes, right?
I think so. Okay, great. 20 minutes plus 5 minutes questions.
Okay. Sure, sure. I will be quicker.
What happened?
No.
Because you want to move that like on my laptop?
No.
Oh,
Hello?
maybe go to the microphone. Questions afterwards.
The microphone working well? Hello?
Yes, what is
Okay. Okay.
You can do the thing I said you were.
I'm not.
Oh, sorry. So I fix your mic.
Okay. Good.
All right.
Can you move this part a little bit?
I'm on as a host.
Yeah, but this may occupy some spaces. We try. Ah, that's perfect. Okay, great.
Let me know when you're ready.
Yeah.
I don't know which Zoom you're in, but it's not the right one. But you're not.
On
Oh,
this
because
second
you,
vote.
because you started, because you joined before, that's the problem.
Why is this a problem?
But you started live before you logged in. So now you're regular. I don't. What's your name? What's your how your? Yeah.
I'm going to stay covered.
Make chat screen. You share your screen?
Yeah. I apologize. I was not.
Oh, okay. How about this one?
Okay. Let's back up. Presentation.
Yeah, can you move this part or? Yeah.
Okay, are we good?
Okay.
Okay. Well, welcome to this session, the first session or parallel session on, well, quantum entropies and their applications very generally. So the first speaker is Haonan Zhang on application, a variational method and its applications. So please.
Okay, thank you very much for the introduction and sorry for the delay, and many thanks to the organizers for giving me this opportunity to speak. So today I will talk about a variational method and its applications in some problems in quantum information theory. Okay. So let's start with three very easy exercises, namely to determine the parameter PQR such that the power function in one variable, two variables, and three variables are jointly concave or jointly convex. So this is certainly a very easy exercise of calculus, and you can do this by computing the second derivative or computing the Hessian matrix, then check if it is positive semi-definite or negative semi-definite. Okay, but this exercise becomes much more involved in this quantum analog. Namely, we are interested in the joint concavity, joint convexity of the following trace functionals. So for example, for this one variable case, we are interested in the parameters P and S such that this trace functional is jointly concave, is concave or convex in A for any matrix K. So namely, the definition is that you take some 2s powers of shorten 2s norm of the product of some power of A and some fixed matrix K. So this is a quantum analog of exercise 1, but this result is very deep and very complicated. So maybe it's better to call it theorem 1. And the proof is not that easy. In principle, you can still repeat the argument of computing second derivative, but in this case, it will be very, very complicated. So we need some new tools and new ideas. And things become much more complicated when it comes to the following two variable case and the three variable case. So let me have a quick look about this trace functional. So for the two variable case, you have some powers of A, some powers of B. If you want, you can also put some any fixed matrix K here. Then you compute the 2s powers of shortened 2s norm. And for the three variable case, it is very similar. And one different feature is that the variable in the middle is linear. It's linear in A. So we don't put extra power here for some reason. So as you can see, this question look very complicated, and we're mainly interested in determining the parameters PQS such that they are jointly concave or jointly convex for any K. So in this talk, I will explain to you why we are interested in such problems. They are certainly a purely mathematical problem, and actually they are related to some problems in quantum information theory, such as the data processing quality and monotonicity properties of various entropy quantities. So in the history, there are some conjectures which are related to this, and these conjectures are eventually becoming theorems. And we will see that a variational method can be very helpful in solving these problems. And this is something that I want to share with you in this talk. And this method is very easy to understand, and I'm looking forward to further applications. So for simplicity, let's work with matrices. So H will always be a finite dimensional cubic space. Okay, So the beginning of the story is a conjecture by Haonan Zhang and Dyson in 1963, which says that for P between 0 and 1, and for any self-adjoint matrix K, the following information quantity SP rho K, which is defined as follows, is concave function in rho. Rho here, frequently you choose to be a quantum state, and you can define it for general positive semi-defined matrices. So mathematically, we're interested in this trace functional in blue, and we want to prove that this is concave in rho for any K. And this conjecture was resolved by Lieb in a very famous paper in 1973. And in this famous paper, Lieb proved, among many others, the following concavity result. So this is what we nowadays call Lieb's concavity theorem, which says for PQ between 0 and 1, such that P plus Q is smaller than or equal to 1, then the following trace functional is jointly concave for any K. So on one hand, this allows us to resolve the conjecture by Haonan and Dyson by choosing Q to be 1 minus P. And on the other hand, this family of trace functional is just a special case of two-variable trace functional that we are interested in. So this is just a very special case of the functionals psi PQS in our theorem 2. Okay, so this result has found many applications in mathematical physics, quantum information, and it has inspired a lot of follow-up works. And I will not report too much about his generalizations and its follow-up work. Let me just mention one result which can serve as a complement, which is kind of a complementary result of Lieb's concavity theorem. So this is a convexity result of Andon, which says that the same trace functional for different parameters P and Q becomes jointly convex. We have jointly convex in A and B and for any K. So we will see that essentially our theorem 1, 2, and 3 will be reduced to these two special cases. Namely, these two results are our building blocks. And what allows us to do this reduction is what we call the variational method. Before explaining that, let me give you some motivations from quantum information theory. So this is a data processing inequality for alpha zeroing relative entropies. So due to the beautiful lecture of Marco, I don't have to explain too much about these entropy quantities and their importance. So namely the two-parameter alpha zeroing relative entropy introduced by and data is a family of quantum analog alpha in relative entropy, whose definition is as follows. You have some powers of rho sandwiched by some powers of sigma. Altogether, you take some power z. So this is the definition of the trace functional here. And when you choose z equals 1 and z equals 1, z equals alpha, then you recover the pace type alpha in relative entropy and the so-called sandwich alpha in relative entropy. So certainly there are some, it also includes many other entropy quantities, which I will not recall here. Here is a very beautiful picture by Philippe summarizing the connection of this d alpha z and then many other entropy quantities. So in this talk, we are interested in so-called data processing inequality, or the monotonicity property of alpha zeroing relative entropies. So recall that the data processing inequality says the quantum relative entropy cannot increase under the action of any quantum channels. So here, namely, we want to determine the parameter alpha z such that this inequality holds for any quantum state rho and sigma and any quantum channel E. Due to the Stein-String theorem, this is essentially equivalent to some concavity and convexity property of trace functionals. Namely, dpi holds for d alpha z if and only if either alpha is smaller than 1 and psi is jointly concave, or alpha is bigger than 1 and psi is jointly convex. Here, this psi is nothing but the two-variable trace functional inside of the definition of d alpha z. So again, this psi is just a very special case of our theorem 2. So the story is that we know some parameters for which concavity or convexity is true, and we know that some parameters the concavity or convexity fails. But there are also some parameters which was not clear to us at that moment. So this motivated Udanat and Data to raise the following conjecture. Namely, for some parameter P and Q, the following trace functional is jointly convex. Or equivalently, for some parameters alpha and z, the data processing inequality is valid. Later on, this stronger conjecture was made by Haonan Zhang and Lieb. Namely, they asked the same joint convexity, but for more general family of trace functionals. Namely, you replace this parameter 1 over P plus Q with more general S. And their motivation is based on the years of the study of the concavity and convexity properties of these trace functionals. And this is only one remaining unsolved case at that moment. So in other words, as long as you could solve these conjectures, then you will obtain the following picture, which is very, very nice. Namely, this picture summarizes the concavity and convexity of this two-variable trace functional. This is nothing but the theorem 2 here. To understand this picture, namely, it says that in this green region, you have the concavity or joint concavity, and in this yellow region and orange region, you have the convexity or the joint convexity. And apart from this, the concavity or convexity fails in general. So our main result is that we may solve the conjectures, we may complete this picture. And so the conjecture concerns this yellow part. But on one hand, our proof is very simple using the variational method. On the other hand, our proof also applies to this green part and the orange part. And the idea can be understood from this picture in a very intuitive way. So namely, we want to reduce the problem in this green part, yellow part, and orange part to what is happening on this red line. Red line here are very -1 to 2. And using the knowledge on red line, we can solve the problem. But actually, you can go much further. You can essentially reduce everything to the building blocks that we mentioned from the very beginning. So namely, the first building block is a special case of Lieb's concavity theorem. Namely, when you choose Q to be 1 minus P, then this trace functional is jointly concave when P is between 0 and 1. Second building block is a special case of Haonan's convexity theorem, which says this trace functional for P between -1 and 0 is jointly convex. In fact, actually, we need also one more fact. For convenience, let me name it building block 3, which says for positive T, the functional trace of a to the power minus T is convex. Okay. So now I want to explain our variational method that allows you to reduce the problem to these building blocks. And the idea is very, very simple. So, namely, we are going to use the fact that the concavity is stable under taking minimum or maximum under certain conditions. So the first fact is that if you have a family of concave function, then the infimum is also concave. The second fact is that sometimes we have very good maximum formulas, but we still want to prove the concavity. In general, this is not true, but it is possible when this function f is jointly concave. So if f is jointly concave in x and y, then taking the infimum over y, then you have a concave function in x. Then we need some variational formula to make this argument work. And this is our key. So namely for any invertible matrix xy and the positive RIs, such that the condition for the Holder's inequality is satisfied, then you have the following minimum and maximum formulas for this piece power of Schatten P norms of the product of x and y. To see that why this is useful. So firstly, the proof is very simple. You simply use a Holder's inequality and you find minimizer and maximizer. On the other, secondly, you can understand the idea in the following way. Suppose that we want to prove the joint concavity in the green region, and this formula allows you to reduce the problem in the red region because it separated the two variables successfully. So two variable case is reduced to the one variable case, which in general it is easier. But you can actually go further. Namely, if you want to prove the concavity in the green region, then you can use a chain of minimum and maximum formula to reduce the problem to building block 1, so the Lieb's concavity theorem. Similarly, you can reduce the yellow region to the building block 2 and orange region to the building block 2 and building block 3, respectively. Therefore, using this variational method, you can solve the conjectures. You can prove the theorem 1 and 2 using only the Lieb's concavity theorem and Dohn's convexity theorem. So this is how you can use this variational method to resolve the conjecture by Wood, Nakadata, Cullen, and Lieb. And now I want to present you some other applications of this variational method. So you can reformulate variational formulas in the way that the minimizer and the maximizer are unique. This allows you to obtain some equality conditions of data processing. And the second application is that you can prove some triple convexity result, which is essentially theorem 3. Theorem 3 is about convexity of 3-variable functionals. And this is related to a conjecture by Alarashid and Zaglensky, which you can prove using complex interpolation. And their motivation of studying this kind of trace functionals is to study something like something called monotone norms, which are some similar notion to monotone metrics, if you have heard of that. And you can also use this to prove some non-convexity result, which I will not explain in more detail. So let me finish with two remarks, or two questions. So I would like to know if one can use these formulas to study, firstly, the stability of quantum function inequalities, because this kind of ideas has been used a lot in the classical functional inequalities, especially with a lot of entropy quantum entropy inequalities. And secondly, whether we can use these kind of variational formulas or duality formulas to study the numerical calculations of entropy quantities using SDB. But this is just a guess. I'm open for any kind of comments or remarks. So with this, I want to conclude my talk, and thank you very much for your attention.
Questions?
Can you expand a little bit as to what you mean by stability of the quantum functional inequalities?
This one. For example, you have data processing inequality, and you can prove something stronger. For example, you can give a lower bound of the difference in terms of some quantity, probably the difference of phase recovery map. Therefore, whenever you have the equality condition, you automatically have the existence of phase recovery map. So, for example, Erica Cullen and Avashanina have some results like this, but certainly their idea is not to use any duality formula, but such idea of duality formula has been used in the classical functional inequalities, for example, by Erica Cullen. So I just wonder if such ideas can be applied in the quantum setting. Thank you.
Okay, thank you. Let's thank the speaker again. We are running a little bit late.